going to put some nasty. This is where there can be some tricky answers. So we're going to open a much more complicated file than the one for the paired t-test, which is largely just two things and dead easy. Almost impossible to get that one wrong. Now, this is the serials data set that I really like a lot. So here, you've got the name of the cereal, you've got the manufacturer, you've got it's hot or cold cereal, calories, protein, fat, sodium, fiber, carbs, sugars, potassium. The thing about this is you've got missing data, like this -1 over here, so you need to check that it's correctly done. Oh, there isn't. It isn't correctly done. I'm not going to be that devious. It will have be correct in having the missing values put in it. Why have I done the non-coded version? In which case, I think I've just done. Let's get rid of that one. I'm going to delete that file, and I'm going to download the one that I've given you and hope that it's the one that's got the coding right in the so I've just downloaded the file again. Let's hope that this one is what I expect, having the missing values in it. Yes, that's what I want. Phew. Right, this is the correct data set, and that will give me the correct values. So a question might be, is there a difference in the mean protein content between cereals made by General Mills and Kellogg's? So that is, I'm checking the difference of means. They're independent of each other, two separate companies making their cereals. So I now need to do an independent samples t-test. Now, that's a bit of a naughty thing to do because I'm picking out a specific question out of a mass of data. And you have to think, why do I want to ask that question rather than any other? So I've just said, what's the mean difference in protein? But I could have done calories or fat or sodium. Why did I pick just that one hypothesis instead of testing all the possible hypotheses within this set of data? But anyway, for the sake of the exam, we're going to do just one t-test within this particular set of data. I do analyze, I do compare means, and I do a slight panic. I do independent samples t-test. So my test variable, I want to test amount of protein, that's fine. And my grouping variable is going to be manufacturer. Now I have to define what the groups are called. Now, let's do something which will probably go wrong. So I'll type Kellogg's. Why did I pick? Okay, I'll do General Mills because that was the one that I mentioned. Well, I was trying to save myself time by doing post because it's got less typing. I do continue and I press OK, and nothing happens. I go, what's happened? So it's empty. It's not found any data. Now the reason for that is because I put in the wrong names. So if I go to data and I don't view the value labels, I've got K and G. And now hopefully, if I change the things that I'm specifying in this to K and G instead of manufacturer define groups, so if I change that to K and this one to G, you continue and press OK, and it works. So you have to define your groups based on what they're actually called within the file, not what you actually see depending on their labels. They're 23. Oh, that's nice. 23 in Kellogg's, there's 22 in General Mills. That's good because you've got about equal sample sizes. The mean amount of protein in Kellogg's is 2.63, mean in General Mills is 2.31. And here is the t-test. Now this is a slightly more complicated table than the one you get for paired. compared to piece of cake. You just go across, you read it, no particular problem. Here, there is a problem. So the first thing that SPSS does is it runs two versions of the t-test. It runs the original formula as devised by students in 1920, and it runs the new improved version, which is called Welch's t-test, which has a big complicated formula for the degrees of freedom. Under the original degrees of freedom thing, the number of degrees of freedom is the two sizes of the groups, each minus 1. So it's 23 minus 1 plus 22 minus 1. So that ends up being, in this case, 43 degrees of freedom. That's a simple way of doing it. Now, the new formula is to take into account this problem of if your variability or variances of these two groups are the same or different. In this case, they're pretty close to identical. But when you have small samples, the variability, the variance, and the standard deviation can be very different between multiple samples. So this bottom formula is more general. It will always work. The top formula is not so good if your two sample sizes are very different to each other and your variance is very different, then it gives you stupid answers. Now, to tell you which one you're supposed to use, it does something called an F test. Now, I have a view about what F stands for. It supposedly stands for Fisher, but I think it probably stands for something else, because I want to ignore it. It's not relevant or important or significant, and I really don't care. Because this Welch's test, which I said is the new version, was devised in the 1930s. Nobody should ever be using the formula that was devised in the 1920s. This bottom line is right. The rest of it should be consigned to history. No one should ever, in science or in papers or in anything, use the original test, because it is biased and wrong. If you've got something better that's been invented and tested and checked out, use the new version. So we use the new version. This has the added thing of you really don't care less what the F test is. You don't care what this is the test statistic for it, and this is its significance. So it's telling you there's no difference between the variances. But it doesn't, so you could read that top level of the table. But we are going to ignore that, and we're only ever going to read the bottom row of the table. So the test statistic under the t-value is 1.017. The degrees of freedom is 42.586. It's non-integer, which makes no sense, but if you see the formula, which is in the lecture notes, then you'll understand. The significance is 0.315. Nowhere near 0.005, so therefore there's no difference in the protein content between cereals from Kellogg's and General Mills. The mean difference is 0.33, whatever it is. The standard error of the difference is 0.328, and the confidence interval for the difference goes between a negative number and a positive number, so it contains 0. If a confidence interval for a difference contains 0, there's no difference between the two groups. So what I'm going to do here is say, what's the test statistic for the t-test, for the difference between these two? What's the test statistic? What's the number? I'm frightened to death. Are they going to get it wrong? Everyone's gone to sleep. Yes, it's 1.017. What am I going to expect people to have done wrong? Which number do I think that they're going to pick, which is the wrong one? So what do you think my wrong answer is going to be? Exactly. So now, because you're here and paying attention, you know what my trick question is going to be. Exactly. So I'm going to have the 4 multiple choice answers are going to be 1.017, 1.019, 0.314, and 0.315. So that's exactly how I'm likely to do it. I might be particularly devious and clever and pick 0.024. But that at least tells me who's awake and who isn't. At least here there are some potential wrong answers that you can miss. With the paired, it's a lot harder for me to see it do anything and make a challenging multiple choice. It's always the bottom row of the table. And that's why what I think of the F test.